In the far outskirts of a galaxy, darkness is not empty. It holds faint streams of stars. It holds thin sheets of cold gas. It holds quiet distortions that linger for ages. Somewhere in that vastness, a black hole can drift without a glow. It leaves no beacon. It leaves a pattern, a softened edge, a kink in a stellar ribbon, a gentle wake through a cloud. Tonight the focus stays calm and close to the evidence. The journey moves from the first signs to the long consequences. It follows gravity's slow handwriting across deep space. A distant glow sometimes arranges itself into a quiet ring around an empty center. A wandering black hole reveals itself most clearly through gravity, because light behaves as if space is gently curved. In a deep field where stars appear steady, a background galaxy briefly stretches into a pale circle. The ring is smooth. One side is slightly brighter than the other. The opposite side thins to a faint thread. Nothing luminous occupies the middle. The geometry alone points to an unseen mass crossing the line of sight for a short time. That single fact anchors the journey ahead. A black hole can be present and influence surroundings while remaining almost perfectly dark. Galaxies seem permanent because their large patterns persist for immense spans. A rotating disk keeps layered structure. Dust lanes trace gentle spirals. A dim halo surrounds the disk in a broad sphere. Most stars repeat long loops that take millions of years to complete. Even so, a galaxy is not a sealed container. It is a gravitational landscape with deep basins and shallow slopes. An object stays bound when its motion cannot climb out of the local basin. A black hole becomes a wanderer when that balance breaks, and its orbit is driven into the outskirts or beyond. The scale shifts inward and the contrast becomes sharp. A black hole has no solid surface. Still, it has a boundary and behavior. The event horizon is the surface from which light cannot return. For a black hole with a mass of about 10 suns, that horizon spans about 30 kilometers. That length resembles a long city block laid end to end. Outside that boundary, paths can still lead away. Inside, every future path leads inward. Close to the boundary, gravity changes steeply with distance. That steep gradient is what stretches passing matter into long threads and thin sheets. A familiar analogy holds the geometry without turning it into myth. A heavy steel ball resting on a stretched sheet makes a shallow bowl. A smaller marble rolled nearby curves inward and changes course. No hands tug the marble. The shape guides the path. The analogy is incomplete because real space has no downward direction. Still, it clarifies why light bends. Light follows the straightest available route through space. When space is curved, the straightest route becomes a curve. The sky ring is the mark of curvature seen at a distance, not a glowing object. That unlock leads to a practical sign. Gravitational lensing is the bending of light by mass. When alignment becomes close enough, a ring forms. When alignment is less exact, the ring breaks into arcs. When alignment is looser still, brightness rises and falls without obvious distortion. The pattern is calm compared with most variable objects. No shock front appears, no hot plume follows. The signal is largely geometric. This makes lensing a clean clue for a dark wanderer. It also explains why confirmations are rare and why a single event matters. In another event, a single background star splits into two faint points for a while. The pair slides together, then merges back into one. The change has no color shift and no flicker. It is a clean signature of gravity acting on light, and it hints at an unseen compact lens. A second visual anchor forms where thin material drifts. A cold ribbon of dust crosses a region where starlight is sparse. The ribbon looks like a faint brushstroke against the dark. As the unseen mass passes nearby, the ribbon develops a gentle shear. The near side curves more than the far side. The ribbon lengthens into a drawn filament. A slight twist forms along its spine, and the edges become uneven. No bright flare follows. The change is written in shape and drift alone. This is tidal gravity in plain form, a difference in pull across a small span. Another small unlock follows from that motion. A wandering black hole can influence an environment even when it stays dark. It can stir delicate systems by gravitational scattering. It can loosen the outer layers of a fragile star cluster over long intervals. It can disrupt the coherence of cold gas and leave low-density corridors that persist until pressure refills them. These consequences do not resemble explosions, they resemble gradual reshaping. The record is left in distributions in widened velocity spreads and in softened density peaks. The path to wandering begins in crowded places. A black hole can form after a massive star collapses. It can also appear after compact remnants merge in a dense cluster. In either case, the new object carries motion shaped by asymmetry and encounters. In tight groups, 3 bodies can briefly share a gravitational exchange. 2 leave more tightly bound, 1 leaves with extra speed. A merger of 2 black holes can also produce a recoil, because gravitational waves can carry momentum away unevenly. The remnant does not need to shine for the kick to persist. A limit of observation arrives here, and it is concrete. The black hole itself is not seen, only secondary effects are seen. Lensing rings and arcs require rare alignment between background light and lens. Dust distortions can be produced by many masses and can be confused with ordinary turbulence. Motions of stars can suggest a close pass, yet similar motions can arise from the general clumpiness of a halo. Even when a signal appears, the mass is entangled with distance. A modest nearby lens can mimic a heavier distant lens, and the true mass remains a probability. The scale shifts outward again from a boundary the size of a city block to a galaxy spanning tens of thousands of light years. Beyond that lies the space between galaxies where stars thin out. In that larger view, wandering becomes part of the universe's slow redistribution of mass. A black hole that remains bound can spend long eras on a wide orbit through the halo, returning only after extended dark arcs. A black hole that exceeds escape can drift through intergalactic space, carrying gravity into regions that may never offer enough gas to announce its passing. The next step is to map the galactic basin itself, and to see how an orbit is lifted out of it. A galaxy looks settled from afar, yet its gravity is a landscape with edges that can be crossed. A wandering black hole appears when its motion climbs out of the galaxy's gravitational basin and does not return on the usual loop. In that region, starlight gathers into a broad disk with thin dust lanes. A dim halo surrounds it like a soft sphere of scattered embers. The disk has a subtle thickness. The halo has a gradual fade with no sharp border. The physical detail that matters is not brightness. It is the way gravity changes with distance. Near the centre, the pull steepens quickly. Farther out, the pull relaxes into a long, shallow slope. A visual anchor forms along that slope. A faint stream of stars curves in a loose arc around the galaxy and then stretches outward into the dark. The stream looks like a ribbon of pale grains. It widens where the pull weakens. It narrows where the pull tightens. The shape suggests an orbit that is no longer closed. It suggests a path that has been lifted toward escape. One small unlock follows from that arc. A black hole does not need a straight shot outward to become a wanderer. A wide elongated orbit can carry it into the halo for long spans, and a later nudge can finish the release. The core concept is the gravitational potential well. It is a measure of how deep the basin is. In plain terms, it is the amount of energy needed to climb away. A second concept sits beside it, and it stays gentle. Escape speed is the minimum speed needed to never fall back. In a galaxy like the Milky Way, the escape speed near the Sun's region is about 500 kilometers per second. That speed could cross the distance from Earth to the Moon in under 15 minutes. The number is not the drama. The meaning is the threshold. Below it, a path remains bound even if it stretches far. Above it, the path does not close and the object continues outward as the galaxy's pull fades. A familiar analogy keeps the threshold calm. Rainwater collects in a mountain basin. Some of it swirls in eddies and stays. Some of it finds a higher channel and spills over a ridge. The basin does not chase the water. The shape of the land decides what returns. In the same way, the shape of gravity decides what remains bound. The analogy also carries a caution. A basin can have many outlets. A galaxy has multiple ways to loosen its hold. The next visual anchor slows down the geometry of a bound orbit. In the halo, an orbit is not a neat circle. It is a rosette that turns slowly. The path loops around, and each loop is slightly rotated. The motion looks like a petal pattern traced in faint dust. The petals widen where speed drops. They tighten where speed rises. A black hole on such an orbit spends most of its time far out, moving slowly. It returns inward, briefly moving faster through the dense regions. That time imbalance unlocks another practical point. Long absences do not mean permanent escape. A wanderer can be only temporarily distant. A bound black hole can hide in the halo for millions of years and still be part of the galaxy's inventory. The scale shift becomes soft here. The event horizon can be the size of a city block for a stellar mass black hole. The orbit that carries it can span tens of thousands of light years. The same object belongs to both scales at once. The small boundary sets the tidal gradient. The vast orbit sets the chance of encounters. The third concept enters only as a texture, and it stays simple. The halo is not empty. It is thin gas-sparse dust and a swarm of old stars. Density falls gradually outward. This gradient matters because it governs visibility. In dense regions, passing material can be stirred and heated. In thin regions, little happens that produces light. A black hole can cross the halo like a silent weight crossing a fog bank. The fog barely notices. Only the faintest distortions appear. Another small unlock follows from that thinness. The most common wandering black holes may never announce themselves through glowing gas. Their primary footprint is gravitational, and it is written into the motions and shapes of other things. A second visual anchor arrives in cold gas that behaves like a delicate fabric. A broad, faint molecular cloud sits in the halo. Its edges are scalloped. Its interior has layered wisps. As an unseen mass passes near, the cloud develops a shallow indentation. The near side compresses slightly. The far side lags behind. The indentation travels along the cloud edge like a slow dent passing through foam. The physical detail is a gradient across the cloud. One side feels a stronger pull. The other side feels less. This differential pull stretches the cloud without tearing it immediately. It also creates a weaker, narrow lane where density is lowered. Over time, pressure blurs the lane and the cloud relaxes. The imprint remains long enough to matter, yet it does not need to flare. A limit of intuition and observation becomes unavoidable, and it is specific. From faraway motion can be inferred only through changes impressed on light. The component of motion toward or away from the observer is easier to sense than sideways motion. Doppler shift means motion changes observed wave spacing. A slow drift across the sky is harder to separate from distance uncertainties. A massive lens far away can mimic a lighter lens closer in. A faint stream can be the aftermath of many influences, not just one. Even a clean arc does not reveal a full three-dimensional path. This is why the boundary between bound and unbound is often probabilistic, not certain. A black hole can be labelled a wanderer by the best current inference, and later be reclassified when more context accumulates. The calm way through the uncertainty is to return to the landscape. A galaxy's potential well is deepest at the centre. It becomes shallower outward. It can also change over time. When a galaxy merges with a smaller companion, the landscape ripples. When a dense cluster evolves, local encounters reshape orbits. When two black holes merge, the remnant can receive a recoil that shifts its place in the basin. In all cases, wandering begins as a change in energy. That change can be small, repeated, and cumulative. The image of the star stream returns. The stream is not a straight line. It is a curve that gradually loosens. It points to a ridge in gravity that has been crossed. The next step is to enter the crowded regions where that energy exchange happens most efficiently, and to watch how close encounters can lift one object outward. In the densest star clusters, motion becomes a quiet crowding where gravity constantly reshuffles who stays near the centre. A wandering black hole can be launched outward by close encounters because energy trades hands during brief passages without any need for light. At this distance, a cluster core appears as a bright knot with a soft edge. The light is layered. The centre is smooth and packed. The outskirts fade into a sparse halo of points. Inside the core, paths overlap in projection. Speeds differ slightly from star to star. The physical detail that matters is the gradient. Gravity is stronger toward the centre. Orbits tighten there. Near misses happen more often. A visual anchor forms in that crowded region. A thin dust veil drifts across the core, and the veil shows a subtle bend as if a heavy presence passes behind it. The bend is not sharp. It is a shallow crease that slides along the veil's length. The crease thickens near the centre. It relaxes toward the edge. That single moving crease unlocks a calm conclusion. The cluster does not need fireworks to reveal a heavy traveller. Shape and timing can carry the evidence. A cluster core can be small compared with a galaxy, and that smallness changes everything. Many globular clusters have cores only about 3 light-years across. That span is like 3 annual cycles of light travel, a length that still fits inside a tiny corner of a galaxy. When so much mass occupies such a small region, typical separations between neighbouring stars become far smaller than in a galactic disk. Paths thread through each other's gravitational influence. The result is not chaos in the dramatic sense. It is steady statistical mixing. The first core concept settles in. A close encounter is a short passage where one body feels another's gravity strongly enough to change its orbit. The change can be small for most encounters, yet small changes accumulate. In the same way that repeated gentle currents can move sand from one shore to another, repeated weak tugs can move energy through a cluster. This analogy stays grounded because nothing decides or intends. Only the distribution evolves. The second visual anchor slows down that energy flow. Near the core, a handful of stars trace curved arcs over time. The arcs look like faint loops on dark velvet. Some loops are tight, some loops are wide. A few loops show sudden kinks where a near pass has altered direction. A small payoff follows at once. The kinks show that encounters are not rare exceptions in the core. They are part of the ongoing architecture. A black hole inside such a core acts like any massive participant in that exchange. It does not announce itself by brightness. It announces itself by the depth of the curve it imposes on nearby paths. A second core concept appears and stays narrow. Gravitational scattering is the cumulative reshaping of orbits by repeated encounters. In plain terms, it is the slow diffusion of speeds and directions caused by many small gravitational nudges. The image remains physical. A region can have a higher speed spread. It can also have more elongated orbits. These changes are not random in detail, yet they are predictable in the large. Over many encounters, energy tends to move toward heavier objects in a particular way. Massive bodies often sink toward the centre because they lose orbital energy through many exchanges. This is not a rule written in stone. It is a tendency, and it depends on the cluster's structure. The payoff here is clear and immediate. The same process that draws a black hole inward also sets up the conditions that can fling it outward. The core becomes a place where heavy participants meet each other more often. When heavy participants meet, the energy transactions become larger. The third visual anchor arrives at the moment of a strong encounter, and it remains calm. 3 compact objects pass through a small volume. Their paths curve sharply. For a brief time, the scene resembles 3 streams of faint points, bending around a shared centre. Then one path opens outward into a long arc. The other 2 settle into a tighter pair. The physical detail is in the geometry. The opening path is less curved after the encounter. Its curvature relaxes as it leaves the denser region. The tighter pair shows the opposite. Their arcs tighten and speed up near their closest approach. A small payoff follows from that geometry. A strong encounter can create a bound pair while ejecting a third participant. No impact is required. No material contact occurs. only the exchange of orbital energy matters. The unique analogy that holds this exchange stays within natural motion. In a braided river, two channels can merge briefly and then split. One branch leaves with a faster current, and the other branch slows into an eddy. Water does not choose. The channel shape and the meeting angle decide. In the cluster, the channel is gravity itself. The meeting angle is the timing of the encounter. The branch that leaves faster can become a traveller to the halo. The halo is quieter. It is darker. It is also a long road because bound orbits can still return. Yet an encounter can push the speed closer to a threshold where return becomes unlikely. A careful scale shift softens the sense of distance. The strongest part of the interaction occurs over a span that can be smaller than the distance between nearby stars in the galactic disk. The consequences of that small span can unfold across tens of thousands of light years in the halo and across millions of years in time. Another visual anchor appears in gas because gas records passing gravity like a slow fabric. A cold filament near the cluster edge has a braided structure. Two strands run parallel for a while. A faint knot sits where the strands cross. As the newly ejected object passes, the knot elongates. The strands separate slightly, and a thin wake forms behind the knot. The wake is narrow and smooth. It fades gradually. The payoff is immediate. Even without a flare, a passage can leave a memory in shape. The memory is not permanent. Pressure and turbulence will soften it. Still, the imprint can last long enough to hint at a recent disturbance. A limit of observation becomes specific and unavoidable in a cluster core. Crowding hides detail. Many orbits overlap in projection. Small changes are easy to miss without long-time baselines. Velocities inferred from light can be biased by unresolved blends and by the fact that only part of motion is directly measurable. A star moving mostly sideways can look slow in one kind of measurement, yet fast in another. A black hole leaves no spectrum to measure. Its mass must be inferred from how strongly it bends nearby paths and from how rapidly nearby speeds spread. The same speed spread can also be produced by other dark remnants or by the collective pull of many faint stars. This uncertainty does not erase the mechanism. It only softens claims about any single case. In the larger view, close encounters act like a steady engine for producing wanderers. Some ejections remain bound and create long halo orbits. Some become unbound and drift away. Both outcomes begin with the same quiet geometry, a brief curvature of paths in a dense knot of light. The next step is to look more closely at the strongest version of this exchange, where three bodies trade energy in a single tight passage, and one leaves with a clean, decisive arc. In a crowded stellar core, three invisible weights can briefly reshape the future of a single orbit. A black hole can be thrown outward when a tight pair transfers energy to a third passerby during one close interaction. At this distance, the core looks like a dense glow with a soft edge. The centre has a smooth brightness gradient, the outskirts thin into scattered points. Motion is not seen as lines. Motion is implied by changing spacing and by subtle shifts in the cluster's balance. A visual anchor settles into the scene. Three faintly separated groups of stars form a temporary pattern. Their apparent centre of curvature shifts over a short interval. One small knot tightens. Another knot drifts outward. A narrow gap opens between them like a slow crease in fabric. The geometry suggests a brief exchange that ends with one participant leaving on a wider track. The first small unlock is simple. The strongest ejections do not come from gentle averaging. They come from rare moments when three bodies pass close enough for gravity to act like a lever. The core concept that frames this lever is the three-body interaction. It is the brief period when three masses influence each other strongly at once. In that short period, energy can be redistributed. The total energy stays consistent. Individual shares can change sharply. Two bodies can end more tightly bound. The third can end with extra speed. This can happen without collision. It can happen without any visible flare. The second concept arrives as the key state. A hard binary is a tight pair whose binding is stronger than the typical kinetic energy around it. In plain terms, it is a pair that is hard to separate. It tends to harden further when disturbed. Each encounter can tighten it. Each tightening can release energy into the surrounding motions. That release is not heat in a glowing sense. It is orbital energy given to something else. The visual anchor deepens with a closer view of curvature. Near the tight pair, the local stellar density shows a subtle hollow. The hollow is a low-count pocket. It is surrounded by a slightly brighter ring of stars. The ring is not a lensing ring. It is a density ring formed by repeated stirring. Inside the hollow paths pass quickly and do not linger. Along one side of the hollow, a thin dust thread becomes stretched. The thread develops a gentle S-shaped shear. The shear slowly relaxes after the passage. The physical detail is the gradient across the thread. One side is pulled harder, and the other side lags. The second small unlock follows from that thread. A close encounter can leave a signature in shape even when nothing shines. Tidal gravity can write in curves and in slight asymmetries. The mechanism that launches a wanderer becomes clearer when the encounter is described in stages. First, a third body approaches the tight pair. Its path is initially a mild curve. As it enters the region where gravity changes rapidly with distance, the curve tightens. The approach is not a straight line. It is a bending arc that depends on the relative timing. Then the third body passes near one member of the pair. During that near pass, the third body can gain speed while the pair loses an equal share. The pair responds by tightening. Its separation shrinks. Its orbital speed rises. The encounter ends when the third body moves far enough away that the pair's influence falls. At that point, the third body carries the extra energy outward. The pair remains as a tighter unit near the core. The ejection is often described as a slingshot, yet the image can remain natural and quiet. A unique analogy fits the exchange without introducing machines. In a fast-flowing stream, two stones can sit close together and create a stable eddy between them. A leaf drifting in can be caught briefly. The leaf can then be flung outward along a faster channel as it exits the eddy. The stones do not move much. The leaf leaves with a changed speed and direction. In the cluster, the stones are the tight pair. The leaf is the third body. The channel is gravity. The payoff in that analogy is immediate. The tight pair becomes tighter because it loses energy. The third body becomes a traveller because it gains energy. The same encounter thus creates both a deepening core resident and a potential wanderer. One number anchors the scale of how compact these decisive moments can be. The closest part of the exchange can occur over a distance of about 100 million kilometres. That span resembles the diameter of a broad interplanetary orbit around a star. Compared with the cluster core, that distance is microscopic. Compared with the event horizon of a stellar mass black hole, it is enormous. The scale shift holds the calm. A boundary the size of a city block can govern tides. A close pass across a space larger than a planetary orbit can decide a trajectory across a galaxy. Another visual anchor arrives as the ejected path becomes visible through its effects. A small arc of stars in the outer core shows a coherent drift. Over time, the arc thins. One point leads the arc and the others lag. The arc aligns with the direction of decreasing density. It passes into a region where the background star field grows sparse. The leading point does not brighten. It does not change colour. Its difference is in motion alone. The arc behind it slowly loses coherence because the cluster's field is no longer strong enough to keep the group compact. The small payoff is clear. An ejection does not create a single sharp trace. It creates a change in the velocity distribution. It creates a tail of outward moving objects that can be found statistically. The consequences for a black hole depend on whether the speed after the encounter exceeds the local threshold for return. If it does not, the black hole becomes a wide orbit traveller. It can spend long spans in the halo and then drift back inward. If it does, it becomes unbound. The galaxy's pull still acts at great distances, yet the path does not close. The black hole continues outward into darker regions where encounters become rare. The physical world around it changes too. Gas density drops, dust becomes thin. The chance of luminous accretion declines. The wanderer becomes harder to notice by light. The signature shifts toward gravity alone. Another small unlock clarifies why tight pairs are central to this story. A loose pair is fragile. Encounters can disrupt it. Energy can be absorbed in rearrangements without a clean ejection. A hard pair is different. It has a reservoir of binding energy. Encounters tap that reservoir and convert it into motion for others. Each successful encounter can harden the pair further. This creates a feedback. The harder the pair becomes, the more energy it can give away per close interaction. The more energy it gives away, the more likely it is to launch fast objects. This does not imply inevitability. It implies a statistical pathway in dense environments. A limit of observation arrives with a concrete edge. The decisive part of the encounter is brief and occurs in a region that is hard to resolve at great distance. Only indirect clues remain. The tight pair itself may not be separable from surrounding light. The third body may be too faint or too blended in the core glow. Motions across the sky require long baselines to measure cleanly. Even when a fast outbound object is identified, its full three-dimensional speed may not be known. The sideways component can be uncertain. The distance can be uncertain. A bound halo orbit can masquerade as an escape. An escape can masquerade as a wide bound orbit for a long time. Mass estimates also remain entangled with distance, because the same apparent curvature can arise from different combinations. This is a limit of inference, not a limit of the mechanism. The calm view is that the mechanism leaves a family of footprints rather than a single stamp. Those footprints include tightened binaries near the core. They include a depleted core region where repeated encounters eject and heat. They include an excess of high-speed objects on radial tracks. They include disturbed gas filaments with gentle shears that fade. The cluster thus becomes both a cradle and a launcher. It can nurture compact pairs. It can also send travellers outward. The next step moves from encounters that trade orbital energy to events that emit energy away from the system entirely, where merged black holes can recoil and shift their place in the galaxy. Some mergers leave no glow behind, yet the remnant quietly shifts position, as if nudged by a passing tide. A merged black hole can recoil and become a wanderer, because gravitational waves carry momentum away in an uneven pattern. In that region, two dark masses circle each other in tight silence. Around them the starfield looks undisturbed. No plume forms, no persistent halo brightens. The only physical trace is in geometry and in timing. A visual anchor appears as a faint expanding pattern in the fabric of space itself. The pattern is not a light ring. It is a subtle sequence of compressions and relaxations that spread outward. Nearby matter would be stretched along one direction and squeezed along another. The stretching has an axis. The squeezing has an axis. The axes rotate as the binary orbits. That rotating quadrupole pattern is the clean signature that energy is leaving as gravitational waves. The first small unlock is immediate. Energy can leave a system without light, and when energy leaves in a directional way, momentum can leave too. The first core concept is gravitational waves. They are ripples in space-time that travel outward at light speed. They do not require material to carry them. They carry energy and momentum as part of their structure. The second concept is the recoil kick. It is the motion of the remnant caused by asymmetric emission of momentum. In plain language, it is a shove produced by a lopsided release. A brief definition keeps the words grounded. Recoil kick means net momentum loss in one direction, and motion gained in the opposite. The analogy that holds the shove stays natural and quiet. A rotating lawn sprinkler can send more water in one direction if a nozzle is partly blocked. The body then feels a gentle push the other way. The sprinkler does not decide. The The nozzle geometry sets the imbalance. In the merger, the geometry is the binary's mass ratio and spin orientations. The waves are the outflow. The remnant responds to the imbalance by moving. This does not imply intention. It is a consequence of conservation. The visual anchor deepens with a slow view of the last orbits. The binary's path tightens. The separation shrinks. The curvature steepens. The orbital period shortens. The surrounding star field remains almost unchanged because the interaction is compact. The signal is carried away in space-time distortion, not in photons. Then a final moment arrives. The two horizons become one. The merged horizon settles into a single surface. Its shape is briefly distorted. It rings down towards symmetry like a stretched membrane returning to rest. The physical detail is a changing horizon geometry. It starts slightly elongated. It relaxes toward a smoother sphere. The small payoff follows from that shape change. The ring down is not decoration. It is the phase where asymmetries fade, and where the last portion of momentum can be radiated away. If that radiation is uneven, the remnant leaves with a net velocity. One number anchors the sense of scale without forcing precision. A recoil can reach about 1,000 kilometers per second in extreme cases. That speed could cross the distance from Earth to the Moon in roughly 6 minutes. The comparison keeps the number tangible. It also points to the consequence. In some galactic environments, that speed can exceed local escape. In other environments, it can lift the remnant into a long halo orbit. The scale shift becomes soft. The shove is delivered in a compact region near a horizon that might span tens to hundreds of kilometers depending on mass. The resulting drift can carry the remnant across thousands of light years over long intervals. A small event on a tiny scale can rewrite a large-scale path. Another visual anchor appears in the wake of the kick, and it stays subtle. A thin disk of gas may have been present around the binary. The disk is not bright and stable. It is a faint cold structure with layered density. After the kick, the remnant is no longer centered. The disk's inner region becomes offset. The density peak shifts to one side. A crescent-shaped overdensity forms where gas piles up. The opposite side thins into a shallow cavity. The cavity has a smooth boundary. Its edge is marked by a gentle gradient in density, not a shock front. The small payoff is clear. Even a dark event can leave an asymmetric imprint in nearby matter. The imprint can persist for some time as the gas rebalances. It can also be erased if the environment is too thin. This explains why such recoils are often inferred rather than witnessed. Another step in the journey passes through the conditions that make the kick large or small. If the merging black holes have unequal masses, symmetry is broken. If their spins are misaligned with the orbit, symmetry breaks further. The gravitational wave pattern becomes more directional. Momentum flux becomes uneven. The remnant responds with a larger recoil. If masses are equal and spins align in a balanced way, emission is more symmetric. The recoil is smaller. The mechanism is thus not a single value. It is a distribution shaped by initial conditions. That unlock matters because it links wanderers to population history. Environments that create many mergers can also create a tail of recoils. Dense clusters can assemble binaries through encounters. Galactic nuclei can bring black holes together through repeated interactions. Each setting produces different typical alignments. Each setting yields different recoil chances. A limit of observation arrives with a clear boundary. Gravitational waves themselves are difficult to localize precisely on the sky. The information carried is rich in timing and frequency, yet position can remain uncertain. The remnant is dark and it quickly leaves the merger site. Any gas imprint can be faint and short-lived. Without a bright electromagnetic counterpart, the kick must be inferred indirectly. The inference can depend on models of how spins align. It can depend on assumptions about surrounding gas. Even in cases where an offset disk is suggested, other processes can mimic asymmetry, including ordinary turbulence and tidal disturbances. This is a limit of triangulation and of resolution, not a limit of the underlying physics. The calm approach is to treat recoil as one pathway among several and to follow its distinct footprints. Those footprints include displaced centers, asymmetric inner structures, and black holes found away from expected locations. Another visual anchor shows how a kicked remnant could appear in a galaxy's light distribution. A faint compact cluster of stars drifts with a slight offset from the galactic center. The central light peak is not perfectly aligned with the dynamical center. A shallow dip exists where a heavier object might have been. The offset is small in angle, it is large in meaning. It suggests that the deepest part of the basin has been disturbed. The small payoff here is immediate. A recoil does not need to eject a black hole entirely to matter. Even a modest displacement can alter the local gravitational gradient and change how stars and gas settle. The remnant may oscillate through the center. Each pass can stir the inner region. Each pass can heat nearby stellar orbits. Over long times, the core structure can be reshaped gently. The section closes by turning from the launch mechanism to the long travel. A recoiling remnant that remains bound becomes a halo wanderer with a history written into its initial shove. The next step is to enter the quieter spaces where a wanderer often remains invisible, and to see why darkness can be the default state for most of these travellers. A wandering black hole often travels through darkness that contains almost nothing to hold on to. A drifter stays nearly invisible because too little nearby material falls inward to warm and glow. At this distance, the halo of a galaxy looks like a thin haze of stars. Between those stars, gas is present but sparse. Dust is present but scattered. The physical world is defined by gradients. Density declines outward. Pressure declines with it. In that quiet, thinning gravity still acts with full seriousness. Yet gravity alone does not produce light. Light appears only when matter is stirred, compressed, or heated. A visual anchor forms in a rare patch of gas. A small cloud floats in the halo like a pale smear against the dark. Its edge is ragged. Its interior shows layered wisps, each wisp slightly offset from the next. As an unseen mass passes nearby, the cloud does not explode. It reshapes. The nearest wisp curves inward and stretches into a narrow ribbon. The far side lags and stays broader. A teardrop-shaped wake appears behind the region of strongest curvature. The wake is faint. It is smooth. It fades gradually into the background. One small unlock follows from that shape. The most reliable sign of a drifter is often geometry in the surrounding matter, not brightness from the drifter itself. The central concept here is accretion. Accretion is matter gradually falling inward under gravity. In a dense environment, accretion can create a hot flow. In a thin environment, accretion can fail to build a steady glow. The difference is not a change in gravity. It is a change in supply. A simple analogy holds that supply without implying intention. A whirl in water forms only when the water is deep enough. In a thin film, the same motion becomes a smear with no depth. A black hole can be the place where a whirl would form. The halo can be the thin film. When the film is too thin, the flow cannot organize into a bright structure. The reason matters immediately. If most drifters move through thin regions, most drifters remain dark most of the time. A second visual anchor settles on the boundary of that wake. The wake has a sharper front edge and a softer tail. The front edge is a shallow arc where gas is slightly compressed. The tail is a longer lane where density is lower. Tiny grains of dust drift within it. The grains do not sparkle, they only outline the flow. The arc shifts slowly as the unseen mass continues onward. The scene suggests a moving disturbance in a medium that resists change. The payoff is quiet and clear. Even when little light appears, the shape of gas can reveal where gravity has passed through. A second concept helps keep the story concrete without adding clutter. The accretion rate is the amount of material arriving per unit time. It is not a fixed property of the black hole. It is an environmental outcome. It depends on local density. It depends on relative speed between the drifter and the gas. It depends on how easily gas can shed angular momentum and slide inward. This is why a drifter can be silent for long eras. It can also become briefly noticeable when it crosses a denser lane. The scale shift is gentle and persistent. Near the event horizon, tides become extreme. Far away, the environment becomes the deciding factor. A boundary the size of a city block can sit inside a region of gas that spans light years. Most of that gas never comes close enough to matter. It flows around the gravitational influence and keeps going. Another small unlock arises from the idea of a threshold. A bright accretion disk requires not only material, it also requires a way to compress and heat that material efficiently. In a very thin halo, gas particles may be too rare to collide often. Without frequent collisions, energy does not easily turn into heat. Without heat, radiation remains weak. The drifter remains a mass in motion, not a beacon. The calm conclusion is practical. Darkness is not unusual in this setting. It is the default. One number anchors how thin the medium can be. In parts of a galactic halo, there can be about one particle in a volume the size of a sugar cube. That is far thinner than air near a sea-level shoreline. The comparison shows why flow behaves differently. Collisions become infrequent. Cooling becomes slow. Any warm patch can fade before it grows into a stable, luminous region. The teardrop wake may appear for a time. It may then dissolve into the background. A third visual anchor arrives when the drifter crosses a narrow filament. The filament resembles a faint thread drawn across a dark field. It has a slight twist. Its center is denser than its edges. As the drifter passes, the filament develops a kink and a stretched section. The stretched section becomes thinner, then fractures into two parallel strands. The strands drift apart by a small angle. The separation increases slowly. This is not tearing by contact, it is shear produced by a gradient in pull across the filament's width. The payoff follows at once. The same tidal field that can stretch matter near a black hole can also spread and thin it enough to reduce feeding. Stretching can starve accretion as easily as it can trigger it. This explains why bright episodes can be brief. A dense knot may pass near and begin to fall inward. Tidal forces can then pull it into a long stream. A stream has more surface and less depth. It can radiate some energy, yet it can also disperse and miss the deepest region. The drifter receives little net supply. The environment returns to quiet. A limit of observation fits naturally into this thinness, and it is specific. In faint regions, small signals are easily confused with background structure. A dim wake can resemble ordinary turbulence. A mild arc can resemble a random density ripple. The time baseline needed to see coherent motion can be long. The background itself evolves. Gas clouds drift. Dust lanes shift. Without a bright, steady counterpart, the identification relies on subtle patterns. It relies on modelling of how gas should respond to a moving mass. It also relies on distance estimates that are often uncertain. A thin wake seen far away can be mistaken for a thicker wake seen nearer. A brief flare can be missed entirely if it fades quickly. This is a limit of sensitivity and resolution, not a limit of the underlying physics. The calm posture is to accept that most drifters are found through rare, favourable alignments of circumstance. When a drifter crosses a denser pocket, the accretion rate can rise for a time. The wake can sharpen, the inner flow can warm. A faint transient glow can appear, and then diminish. When a drifter returns to the thinnest halo, the glow can vanish again. Over millions of years, this alternating pattern can repeat. The drifter becomes a quiet traveller whose presence is measured by what is disturbed and what is bent. The next step moves closer to the most physical mark of passage. A thin stream becomes a stretched thread. Tidal forces become visible as shape, and the geometry of stretching begins to tell its own story. A thin strand of gas can look calm until a hidden mass passes close enough to pull it into threads. Tidal forces reveal a wandering black hole by stretching matter unevenly across small distances. At this distance, a cold filament drifts through a dark region like a pale ribbon laid on velvet. Its edges are frayed. Its centre is denser and slightly darker. Fine dust within it creates faint layering. The layering is not uniform. It shows subtle knots where density collects. A visual anchor settles on one knot. The knot is oval. It has a brighter rim and a softer interior. As the unseen mass approaches, the oval rim begins to elongate. One end sharpens into a tapered point. The other end broadens into a flattened fan. The filament's center line bends toward the passing gravity. A narrow gap opens behind the knot like a small hollow carved into fog. The first small unlock is immediate. The stretching is not random turbulence. It has direction. It aligns with the path of the parser and the gradient of pull. The core concept is the tidal field. It is the difference in gravitational pull across an object. In plain terms, it is how gravity pulls harder on the near side than the far side. One sentence holds the definition and stays short. A tidal field is gravity changing noticeably across a small distance. The image returns quickly to keep it tangible. A soft loaf of bread can be pulled from both ends. The center thins into a long strip while the ends remain thicker. The bread does not need to be cut. The pull alone changes its shape. In the filament, the near side of the knot is pulled more strongly. The far side is pulled less. The knot elongates. The filament becomes a drawn thread. This matters because the shape change carries information about the parser's mass and distance. A second visual anchor forms along the stretched thread. The thread becomes narrower than the original filament. Its surface shows faint striations. The striations run parallel to the length like comb marks in sand. Along the outer edge a delicate curl forms. The curl is a thin arc that peels away. The arc rolls into a loop and then unwinds. The loop is not stable. It relaxes as the flow continues. The physical detail is the gradient across the thread's width. The near edge accelerates slightly. The far edge lags. The result is shear. The shear produces a twist that travels along the thread like a slow wave. A small payoff follows from that twist. A tidal encounter can create both stretching and rotation in nearby gas, and the rotation can be a clue to how close the passage is. The second concept enters with care and stays simple. Angular momentum is the tendency of a rotating system to keep rotating. In this setting, it is the reason material often misses the deepest region. Gas that begins with sideways motion cannot fall straight in. It must shed that sideways motion to move inward. If it cannot, it wraps into streams and arcs instead. This clarifies why a filament can be strongly distorted without producing a bright, steady disk. The distortion is a near miss. It is a glance, not a capture. The analogy remains natural and unique. A slow river meets a rock and divides into two channels. The channels curve around the rock and rejoin downstream. The rock does not need to move. The flow pattern changes because the obstacle shapes the path. In the tidal encounter, the obstacle is not a solid body. It is a steep gradient in gravity. The flow curves because the near side is guided more strongly than the far side. The small unlock is clear. Curving does not imply collision. It implies differential guidance. One number anchors how narrow a stretched stream can become. A filament that begins as a cloud across a light year can be drawn into a stream only a few million kilometers thick. That thickness resembles several times the diameter of a large star. The scale shift stays gentle. A change on the scale of stellar diameters can arise from a disturbance spanning a light year. The same object that imposes the disturbance may have an event horizon comparable to a city block. The extremes coexist in one quiet passage. Another visual anchor arrives at the boundary where the stream begins to break. The stream is not perfectly smooth. Small density beads appear along it. The beads are regularly spaced. Each bead is a faint swelling, with a sharper front edge and a softer tail. The swellings drift apart slowly as the stream lengthens. The physical detail is layering. A denser core forms inside each bead. A thinner sheath surrounds it. The beads suggest that the stream is not only being stretched, it is also becoming unstable to its own gravity and pressure. A small payoff follows at once. Stretching can create conditions where matter fragments into clumps, even while it is being pulled apart overall. This is a gentle paradox that remains calm. The same encounter that thins a structure can also seed new substructure within it. The third concept enters as lightly as possible. Compression is a local increase in density caused by converging flow. It can occur at the front edge of a wake. It can occur where the stream bends. It can also occur where shear folds material together. Compression matters because it governs whether any transient glow might appear. In thin environments, compression may still not produce much light, yet it can alter chemistry and cooling. It can also leave a lasting density mark. The story pauses at a limit of observation, and it stays specific. The stream's thickness and bead spacing can be hard to measure at great distance. Projection can make a narrow structure appear wider. A stream tilted toward the line of sight can be mistaken for a clump. Distance uncertainties can shift inferred sizes by large factors. The same curved wake can be produced by different masses at different distances. In addition, other sources of shear exist, including tidal forces from the galaxy as a whole. Separating a local passer from the background field can require careful modelling. The modelling depends on assumptions about the gas temperature and on how turbulence behaves. This is a limit of inference from shape alone, not a failure of the mechanism. The calm answer is to look for consistent patterns across many structures. A passage by a compact mass tends to create a narrow stream with a smooth directional curve. It tends to leave a wake with a sharp leading arc and a fading tail. It tends to produce shear aligned with the trajectory. Over time, the stream relaxes, the beads disperse, the wake fills in, yet the memory can persist long enough to be found in surveys of halo gas. The scale shift widens once more. In a few million years, a wanderer can cross many such filaments. Each crossing can leave a small reshaping. In a billion years, those small reshaping events can alter how cold gas is distributed in the outskirts of a galaxy. The section closes by turning from gas to light itself. When matter is too thin to glow, light from background stars can still be bent. The next step follows that cleaner signature. It watches how a background star brightens without changing colour, and how that brief brightening can reveal an unseen traveller. A single star can brighten and fade while remaining the same colour and the same shape. Gravitational microlensing reveals a wandering black hole because gravity bends light without adding any light of its own. At this distance, the background field appears steady. Points of starlight hold their places. The darkness between them looks unchanged. Then one star begins to rise in brightness. The rise is smooth. The peak is rounded. The fall is smooth again. No flicker appears. No new glow spreads around it. The physical detail is in the symmetry of the change. The light curve has a clean arch. It resembles a bell shape drawn with gentle slopes. A visual anchor forms around the brightening star. Faint background speckle becomes slightly stretched into a tiny arc on one side. The arc is not a ring visible to the eye. It is a subtle distortion in the pattern of faint sources. The arc grows as brightness rises. It weakens as brightness falls. One small unlock arrives immediately. When brightness changes without colour change, the cause is often geometry rather than physics inside the star. The core concept is gravitational microlensing. It is temporary magnification caused by a foreground mass passing near the line of sight. In plain terms, the mass acts like a lens made of gravity. Light does not bounce off it. Light passes near it and bends. The bending changes where rays go. Some rays that would miss the observer are redirected. The star appears brighter for a time. A short definition keeps the idea clean. Microlensing is brief, brightening from gravity, not from the source itself. The analogy that holds the effect stays simple and unique. A smooth glass marble placed above a patterned cloth can concentrate the pattern into a brighter patch. The cloth does not change. The marble does not glow. The geometry creates the brightening. In microlensing, the star is the cloth pattern. The black hole is the marble. The observer is simply the place where the concentrated rays arrive. The payoff is clear. A black hole can be detected without any gas and without any flare as long as alignment occurs. A second visual anchor slows the moment of closest approach. The brightening star reaches its maximum. The surrounding star field looks subtly warped. The warp is localized. It is strongest closest to the star's apparent position. It fades outward over a small patch of sky. The edges of the warp are smooth. There is no sharp boundary. The sky itself is not disturbed. Only the mapping between positions and light shifts. Then the maximum passes. The warp relaxes. The field returns to its previous appearance. The small unlock follows from that relaxation. Microlensing is reversible because it is a geometric mapping. Once the lens moves on, the mapping returns. The second concept is the Einstein radius, introduced gently and kept brief. It is the characteristic angular scale of lensing for a given mass and distance. In plain language, it sets how close alignment must be for strong magnification. It also sets the size of the distortion region. The term is used once and then folded back into imagery. A bigger mass produces a larger effective lensing region. A smaller mass produces a smaller region. This matters because it ties duration to mass. A heavier lens generally produces a longer event, all else equal, because it influences light over a larger region. One number anchors that sense of duration without turning it into calculation. A microlensing event caused by a stellar mass black hole can last about a year. That span resembles the cycle of seasons on Earth, long enough to be noticed as a slow brightening and fading. The comparison is simple. It shows why these events do not look like sudden bursts. They are slow arcs in time. The scale shift stays calm. The bending occurs over distances near the lens that are vast compared with an event horizon. Yet the effect is measured in the brightness of a point source across a year. A city block scale boundary can be linked to an annual scale light change across interstellar distances. Another visual anchor appears in the path of the lens itself, expressed through motion on the sky. The brightening does not remain centered. The apparent position of the source shifts slightly during the event. The shift traces a small loop. The loop is tiny and smooth. It does not imply the star has moved. It implies the light centroid has moved because the lens creates multiple distorted images. Those images are usually unresolved. They're weighted average shifts. The small payoff is immediate. Even when images cannot be separated, the centroid motion can add information about mass and geometry. This helps distinguish a black hole lens from a lighter object. It also reduces ambiguity in distance. Yet ambiguity remains, and it deserves a clear limit of observation. Microlensing is a rare alignment. Most black holes never pass close enough to a background star's line of sight to produce an event. Even when an event occurs, the lens distance can be uncertain. The source distance can be uncertain. The relative motion can be uncertain. The same light curve shape can be produced by different combinations of mass and velocity. Blending adds another complication. In crowded fields, extra unresolved starlight can dilute the magnification. That makes the event appear smaller than it is. This is a limit of inference from brightness alone. It is also a limit of angular resolution, because the multiple images are typically separated by tiny angles. Without resolving them, the model must carry the burden. The calm approach is to combine clues. Duration suggests mass. Centroid shift suggests mass and geometry. The absence of color change suggests lensing rather than intrinsic variability. The absence of nearby luminous matter suggests a dark lens. Together, these clues can point to a black hole. A fresh unlock follows from what microlensing does not require. It does not require gas to fall inward. It does not require a disk. It does not require a flare. This means microlensing can detect drifters in the quiet halo where accretion is weak. It can also detect them in intergalactic space if a background field is rich enough. The method thus complements searches for luminous transients. Another visual anchor brings the scene outward into a wider context. A dense background field sits behind a foreground halo. The brightening star is one of many. Over long monitoring, a handful of such arcs appear at different times. Each arc rises and falls with its own pace. Each has its own peak. The field becomes a slow calendar of alignments. Most days show nothing. Some days show the beginning of a rise. The payoff is gentle. A population that is otherwise invisible can be counted statistically through these rare events. The count can be turned into an estimate of how many dark masses roam through the halo. It can also hint at their mass distribution. This does not produce a map of individual paths. It produces a census. It produces probabilities and rates. That limitation is part of the method's nature. The section ends by turning from detection to consequence. If a drifter passes close to stars, it can leave more than a lensing arc. It can alter orbits and launch stars onto unusual paths. The next step follows those footprints. It watches for stars whose speeds and directions no longer match their neighbourhood, and it asks what kind of close passage could have made them so. A calm sky can hide a sudden change in motion that only becomes clear when many stars are compared together. A wandering black hole can be traced by the unusual speeds it leaves behind, because close gravity encounters reshape orbits long after the drifter has passed. In that region, a loose association of stars spreads across a dark background. The stars do not form a tight cluster. They share a similar distance. Their colours vary gently. Their distribution looks ordinary until motion is considered. A visual anchor settles on a quiet arc of stars along the edge of a faint cloud. The cloud has a smooth boundary on one side and a frayed edge on the other. Along the smooth boundary, several stars show a subtle alignment in direction. Their paths are not seen as lines. Their paths are suggested by a coherent drift of positions over time. One star near the centre of the arc stands out. Its motion differs. Its trajectory is more radial, pointing away from the group. The first small unlock is immediate. A single fast star is less convincing than a pattern of disturbed neighbours. When a drifter passes close, it leaves a local signature in the velocity field. The core concept is gravitational scattering. It is the change in a star's orbit caused by a close passage near a massive object. In plain terms, it is a flyby that bends a trajectory and changes speed. This does not require impact. It requires proximity and timing. The second concept is hypervelocity. It is a star moving fast enough to escape its home region. A short definition keeps it clean. Hypervelocity means a star travels faster than local escape. The scene slows into another visual anchor to show what the bending looks like in space. Near the drifter's path, faint dust grains form a narrow lane. The lane is not bright. It is a slightly darker strip where density is lower. Along that strip, a few small knots of gas appear, stretched each knot pulled into a short comma shape. The comma heads face the same direction. The tails fade behind them. This is a physical detail of a wake. It marks a moving influence. A small payoff follows from the commas. When multiple features point the same way, the passage has a direction. Direction narrows possible explanations. A drifter passing through a region is not a random event in the local frame. It is a moving centre of gravity that leaves an oriented imprint. One number anchors what counts as unusually fast without forcing a catalogue of cases. A star moving at about 1,000 km per second is fast enough to cross the distance from Earth to the Moon in roughly 6 minutes. That comparison keeps the speed tangible. It also shows why such a star does not remain near its birthplace for long. In a few million years, it can traverse large portions of a galaxy's halo. The scale shift stays gentle. The close encounter that sets the speed can occur over a distance comparable to an interplanetary orbit around a star. The resulting travel can span tens of thousands of light years. The local and the galactic are linked by one brief curve in a path. The analogy that holds the mechanism stays natural and unique. In a calm pond, a drifting leaf passes near a slow whirl. The leaf's path bends, then it shoots out along a new direction. The pond surface does not splash. The leaf simply exits with a different glide. The whirl does not chase the leaf. The geometry of flow sets the outcome. In the gravitational version, the drifter is the whirl. The star is the leaf. The curved path is the signature. This matters because it clarifies what is being searched for, not brightness, not a wake alone, a coherent change in velocity with a plausible curvature history. Another visual anchor appears in the distribution of speeds across a small region. Imagine a patch of halo where most stars have similar velocities. The velocity vectors form a gentle field. Then a narrow stripe appears where stars have slightly higher dispersion. The stripe aligns with the earlier dust lane. The stripe is not a filament of matter, it is a filament of motion. The ends of the stripe blur into the background, the middle is sharper. This suggests a passage that was closest in the centre and weaker toward the ends. The small payoff is immediate. A drifter can be mapped indirectly as a trail in phase space even when it leaves no luminous trail in gas. The mechanism becomes clearer when a simple encounter is described. A star approaches the drifter with some relative speed. Gravity bends the star's path. If the approach is close enough, the bending is strong. The outgoing path can be very different from the incoming one. The speed can also change relative to the galaxy, because the drifter itself is moving. Energy can be exchanged in the galaxy's frame. This is why a moving drifter can accelerate a star and launch it outward. The encounter is like a brief handoff of orbital energy, yet no hand is present, only timing and motion. Another visual anchor slows to show the geometry of a near miss. The star's path curves into a tight arc near closest approach. The arc has a smallest radius at the point of strongest pull. The arc then opens. The curvature decreases steadily as the star departs. In the surrounding field, other stars show smaller arcs. Their deflections are weaker. Their speeds are slightly altered. The pattern resembles a fan. The fan opens away from the drifter's path. The physical detail is the gradient in deflection with distance from the track. The small payoff follows from that fan. A gradient in deflection provides a scale. It can indicate how close the drifter came to the group. It can also indicate whether one massive object or many smaller objects are responsible. Many small objects produce a more mottled pattern. One massive passer produces a smoother, more coherent fan. A limit of observation arrives and stays specific. Velocities are difficult to measure in full 3 dimensions. Motions across the sky require long baselines. Motions along the line of sight require spectra, and spectra can be weak for faint halo stars. Distance uncertainty can convert a modest proper motion into a large velocity error. Blending in crowded fields can shift position measurements. In addition, the galaxy itself has substructure. Streams and shells already produce coherent motion patterns. A star that seems unusual may belong to a tidal stream rather than a scattering event. This is a limit of classification and of incomplete phase space information. It is also a limit of modelling because the distribution of halo motions is not perfectly known. The calm response is to use consistency. A scattering trail should align with other traces. It should align with a weak wake in gas if gas is present. It should align with an overdensity of microlensing events over long monitoring if the drifter population is high. It should also produce a local excess of outward moving stars that are not explained by known streams. Another small unlock clarifies why the footprint can persist. A star keeps the speed it gains. It carries that memory for millions of years. Gas forgets faster because it mixes. Stars do not mix as quickly. Their trajectories remain as long arcs in the halo. This makes stellar motions a long-term archive of passages that are otherwise silent. The scale shift widens again to the galactic halo. Over 1 billion years, repeated passages by wandering black holes can add a faint background of heated motions. The halo's velocity dispersion can rise slightly. Outer clusters can be puffed up. Fragile structures can be softened. None of this needs a bright flare. It is cumulative geometry. The section closes by turning from stars to brief flashes of light. Stellar motion stores memory for long times. Yet a drifter can also produce short transients when it finally meets a denser pocket of gas. The next step follows those rare moments when accretion briefly brightens and then fades back into the dark. A brief flare can appear in a quiet sky and fade before any long structure has time to form. A wandering black hole can create a transient glow when a small pocket of gas is briefly forced inward and heated. At this distance, a dim halo region contains a thin haze of material. Most of it drifts without drama. Then a compact cloudlet crosses the drifter's path. The cloudlet is not large. It is a soft lump with a brighter rim and a darker centre. Its edge is scalloped. Fine dust within it forms faint layers like overlapping veils. A visual anchor settles on the moment the cloudlet begins to deform. The near edge accelerates inward. The far edge lags. The cloudlet elongates into a curved tongue. The tongue narrows toward its tip. Behind it, a shallow cavity opens where density drops. The cavity boundary is smooth. It looks like a bowl pressed into mist. The first small unlock is immediate. A transient does not require a stable disk. It can be the short-lived result of one close passage through a denser patch. The core concept is transient accretion. It is a temporary inflow of matter that does not persist. In plain terms, it is feeding that starts and stops. The start is set by encountering material. The stop is set by the material running out, dispersing or missing the deepest region. A simple analogy holds the temporary nature without invoking machinery. A dry sponge can darken when a small splash lands on it. The dark patch spreads, then fades as the water moves and evaporates. The sponge is not refilled by itself. The patch depends on the splash. In the same way, a black hole can brighten briefly if a splash of gas arrives. The brightening fades when the supply ends. This matters because most wanderers spend their lives in regions where no splash arrives. Their rare splashes become the moments of visibility. A second visual anchor forms where inflow becomes heat. The curved tongue of gas approaches a tighter region. It forms a thin stream with a sharp front edge. The front edge brightens slightly, not as a flame, but as a warmer glow. The glow is concentrated in a small knot. The knot has a bright core and a softer halo. The halo fades quickly outward. The physical detail is a gradient in brightness. It peaks near the inner region and drops with distance. This is the signature of heating by compression and by frictional interactions in the flow. The second concept enters carefully and stays simple. The accretion flow is the moving pattern of gas around the compact mass. It can be disk-like if angular momentum is high. It can be more spherical if angular momentum is low. In transient cases, it is often lopsided. It can be a partial arc rather than a full ring. It can be a stream that wraps partly and then breaks. This helps explain why the glow can be asymmetric. A glow spot can appear on one side of the passing track. The opposite side can remain dark. The small payoff is immediate. Asymmetry is not a flaw in the story. It is expected when the supply arrives from one direction and is torn into a stream. One number anchors the sense of briefness in a way that is easy to hold. A transient flare can last about a day. That duration resembles a single sunrise to sunrise cycle. The comparison keeps the time human-sized without introducing people. It also clarifies why the event is easy to miss. In a halo where years can pass without any change, a one-day flare is a blink. The scale shift remains gentle. The heating occurs close to a compact region that may be only tens of kilometers across at the horizon. Yet the visible effect is measured across a day and can be seen across interstellar distances. A small region can influence what light does far away. Another visual anchor shows what the flow looks like as it fades. After the peak, the bright knot softens. The core dims first. The outer halo lingers briefly. The stream becomes more diffuse. The sharp front edge relaxes into a blur. The bowl-shaped cavity behind the stream begins to fill as surrounding gas drifts back. The layers of dust inside the cloudlet lose their contrast. The region returns toward its previous state. The small payoff is clear. The end of the flare carries information. A rapid fade suggests a short supply or a fast dispersal. A slower fade suggests a longer tail of material still spiraling inward. This can help distinguish a drifter encounter from other transient sources. The unique analogy that holds the rise and fall stays within natural flow. A narrow inlet can briefly feed a tidal pool during a passing swell. The pool brightens with suspended sand, then the water retreats, the sand settles, the pool clears again. The swell is not permanent, the pool does not remain stirred, the clarity returns because the driving input ends. In the same way, a transient accretion episode is a passing swell of supply. The flare is the stirred phase, the fade is the settling phase. The story pauses at a limit of observation that remains specific. A flare alone does not identify a black hole. Many processes can cause brief brightening in the sky. Even if colour remains stable, dust can redden and confuse interpretation. Even if the flare is isolated, the distance can be uncertain. Without precise localization, a background source can be misassigned. In faint regions, the baseline is hard to establish. Small changes can be lost in noise. When the flare is over, the drifter leaves no luminous marker. The inference then depends on modelling of how gas would respond to a compact parser. It depends on assumptions about gas density and relative velocity. It depends on whether the flare duration is consistent with a black hole mass or with a smaller object. This is a limit of ambiguity and of incomplete context. The calm approach is to combine footprints. A transient near a region with a microlensing event history strengthens the case. A transient near a region with disturbed gas geometry strengthens the case. A transient near a region with an excess of perturbed stellar motions strengthens the case. Together, these clues can point to a wandering black hole encounter rather than a random flare from elsewhere. Another small unlock clarifies why these events are sparse. Most of the halo is too thin. A drifter can cross long distances without meeting a dense pocket. When it does meet one, tidal forces can also tear the pocket apart. Much of the material can be stretched into a stream that never fully settles inward. The flare can be brief even when the pocket is present because capture is inefficient. The environment then returns to quiet. Over long times, this pattern repeats. Long darkness, rare short glows. The larger consequence is subtle. Each transient compresses and heats gas locally. It can change chemistry. It can alter dust grain survival. It can create small cavities and wakes that persist for a while. Yet the main story remains the same. Most wanderers remain dark and their brightest moments are short. The next step turns from these brief episodes to slower cumulative effects on star clusters and halo structure. It follows how repeated passages can heat and loosen fragile systems over immense spans of time. A star cluster can look unchanged for ages while its internal motion quietly warms and loosens. A wandering black hole can heat and expand clusters through repeated flybys because each close passage redistributes orbital energy without any light. At this distance, a globular cluster appears as a soft sphere of starlight. Its brightness rises toward the centre. Its edge fades into a sparse halo. The physical detail that matters is the profile. The core is dense and smooth. The outskirts are grainy with isolated points. A visual anchor settles on the cluster's outer boundary. A thin, faint tidal tail extends away like a pale brushstroke. The brushstroke is not uniform. It contains tiny clumps. It also contains gaps. The tail's inner edge is sharper than its outer edge. This asymmetry suggests ongoing stirring. The first small unlock is immediate. A cluster does not need a single catastrophic event to lose stars. Slow heating can leak stars outward and build a tail over time. The core concept is dynamical heating. It is the increase of random motion in a system due to repeated gravitational encounters. In plain terms, it is the gradual widening of orbits caused by many small kicks. The kicks can come from interactions inside the cluster. They can also come from external parsers. A wandering black hole acts as an external parser with an unusually deep gravitational well. It does not need to enter the core to matter. A close pass near the outskirts can still add energy to outer orbits. Those orbits are already lightly bound. A small boost can move a star from a closed orbit to a drifting escape. The analogy that holds this slow warming stays gentle and unique. Fine powder on a flat surface can remain piled until a series of faint taps occurs nearby. Each tap is small, yet the edges begin to creep outward. Grains that were barely stable begin to slide. The pile becomes wider and flatter. In the cluster, the grains are stars. The taps are gravitational flybys. The pile's widening is the cluster's expansion. This matters because it predicts where the first losses occur. The cluster's outskirts respond first. Another visual anchor arrives within the cluster itself. A subtle hollow appears in the star count near the centre. The hollow is not empty. It is a modest lowering of density compared with a perfectly smooth profile. Around it, a slightly brighter ring appears where stars spend more time at their orbital turning points. The ring is not a luminous ring. It is a statistical ring in density. This physical detail points to core evolution. Repeated interactions can flatten the central density. They can also change how energy is shared. The small payoff is immediate. Core structure encodes the history of encounters. A more expanded core can indicate sustained heating, not just initial conditions. The second concept enters with care and stays narrow. Relaxation is the gradual reshuffling of energies and orbits through many encounters. In plain terms, it is how a cluster slowly forgets its initial arrangement. Relaxation time varies with density and size. In a dense cluster, it can be short compared with the cluster's age. In a loose association, it can be long. A wandering black hole can shorten the effective pathway to change by adding stronger encounters than typical star-to-star interactions. This helps explain why some clusters show tails and expanded cores in environments where gentle tides alone seem insufficient. One number anchors how slow this heating can be while still being important. Over about 1 billion years, many small flybys can cumulatively reshape a cluster. That span is like 1/10 of the age of the oldest clusters, a long interval that still fits within cosmic history. The scale shift stays calm. A single flyby lasts only a short time compared with an orbit, yet the memory of that flyby remains in altered velocities. Over billions of years, those velocity changes add up. The cluster's profile shifts from compact to slightly puffed. Its boundary becomes more porous. Another visual anchor shows the moment of a flyby in the outskirts. A dark passer moves near the cluster's edge. The stars closest to the path experience a stronger pull. Their orbits become slightly more elongated. A faint fan of deflections forms in velocity space. In physical space, this appears later as a slight anisotropy. More stars drift outward along one preferred direction. The tidal tail grows clumpier along that direction. The small payoff follows from the fan. A single passer can leave a directional bias that persists for many orbits, because outer stars move slowly and are weakly bound. The direction of the tail can thus hint at the direction of the perturber's passage. The physical detail of the tail becomes more specific. The tail is not a smooth ribbon. It shows bead-like overdensities separated by quieter gaps. Those beads arise because stars leave with slightly different speeds. Faster escapers move ahead, slower escapers lag. Over time, the tail stretches. The beads spread into a longer sequence. The outer edge of the tail frays into isolated stars. The inner edge stays sharper because it is continually replenished. The small payoff is immediate. Tail texture is a clock. The spacing of beads hints at how long the leak has been active. It also hints at whether losses come from steady trickle or from pulses. A wandering black hole passage can produce a pulse by briefly increasing escape rates, even if the long-term leak remains steady. The limit of observation arrives and stays concrete. Tail detection requires depth and wide coverage. Faint tails can blend into the background field. Foreground and background stars can confuse membership. Proper motions can help, yet proper motion measurements become uncertain for faint stars at large distances. Distance uncertainties can smear the tail in 3 dimensions. In addition, galaxies create tidal fields that also produce tails. Separating tails caused by ordinary galactic tides from tails boosted by passing compact masses can be difficult. The models require assumptions about the cluster's orbit and about the distribution of dark objects in the halo. This is a limit of attribution. It is not always possible to assign a single cause. The calm approach is to look for additional clues. A passage by a compact mass can create localized heating and a sudden change in tail direction. It can also create asymmetries in the cluster's velocity dispersion that are hard to explain by smooth tides alone. It can leave behind a deficit of binaries in outer regions if encounters disrupt them. These patterns are subtle, yet they can converge when many clusters are compared. Another small unlock clarifies why this matters beyond one cluster. Clusters are long-lived tracers. Their structural changes record the cumulative gravitational environment of a galaxy. If wandering black holes or common clusters should show a broader distribution of core sizes and tail morphologies, some clusters should appear unusually puffed for their orbital history. Some tails should show directional kinks that align with plausible passages. The scale shift widens again. A drifter's passage near one cluster is a local event. Over a galaxy's lifetime, many clusters can be visited. The cumulative effect can slightly reshape the distribution of halo clusters. It can also add diffuse stellar debris to the halo, contributing to its faint glow. None of this requires bright accretion. It is gravity writing slowly into structure. The section closes by moving from clusters to the broader halo environment. If wandering black holes heat clusters, they also heat the diffuse stellar halo and can soften fragile streams. The next step follows those long, delicate streams of stars and asks how a hidden parser can blur their sharpness without ever being seen directly. A stellar stream can appear like a delicate pencil line across the halo, sharp enough to feel fragile. A wandering black hole can blur and kink such streams because a single close passage adds a localized twist that persists for ages. At this distance, a stream stretches across a dark field in a long arc. Its width is narrow, its brightness is low. The stars within it share a coherent motion. The physical detail that stands out is the stream's edge. One side is crisp, the other side is slightly feathered. Along the center line, a faint density ripple repeats like gentle beads on a string. A visual anchor settles on one segment of the stream where the line is interrupted. The interruption is not a gap of nothing, it is a thinning. The stream becomes wider and dimmer over a short length. The center line bends slightly. A shallow S-shaped kink appears. The kink is smooth. It has a gentle curvature that changes sign once. The edges remain continuous. Yet the line no longer points as cleanly as before. The first small unlock is immediate. A kink does not require the stream to break. It can be the signature of a flyby that rearranges velocities by a small amount. The core concept is stream perturbation. It is the change in stream shape caused by a passing mass. In plain terms, it's a localized deflection that later stretches into a visible feature. The stream is made of stars on similar orbits. A parser changes those orbits slightly in a small region. After that, the altered stars drift ahead or lag behind. The perturbation spreads along the stream like ink spreading along a line. The analogy that holds this spreading stays gentle and unique. A long ribbon laid on still water can be nudged by a fingertip at one point. The nudge creates a small wave in the ribbon. The wave travels along the ribbon and slowly broadens. The fingertip is gone, yet the wave remains as a memory. In the halo, the ribbon is the stream. The fingertip is the wandering black hole. The wave is the kink and the widening. This matters because it provides a way to infer unseen masses from stream morphology alone. A second visual anchor forms where the stream shows a gap-like structure. The density beads become uneven. One bead becomes stretched into two. Between them, a shallow underdensity appears. The underdensity has tapered ends. It is not a sharp notch. Its edges are smooth and rounded. The stream on either side remains aligned. The gap region also shows extra fuzz stars slightly displaced from the center line. The physical detail is the widening of the stream's cross-section in the perturbed region. The small payoff follows at once. A parser can create both a density dip and a local widening because it changes velocities in different directions. Some stars are pushed slightly outward from the stream's plane, others are pushed forward or backward along the orbit. The result is a feature that combines shape and density. The second concept enters with care and stays narrow. Phase mixing is the gradual spreading of initially nearby orbits over time. In plain terms, it is how a small velocity difference becomes a large positional difference after long travel. Phase mixing is why a brief encounter becomes a long feature. The encounter is localized in time. The feature grows in space as stars drift along their orbits. This also explains why streams are sensitive detectors. Their initial width can be small, their coherence can be high. A small disturbance can stand out for a long time. One number anchors how long such memory can last. A stream feature can persist for about 1 billion years. That span is like 10 times longer than the age of many surface features on a rocky planet. It is a slow archive. The scale shift stays calm. The encounter itself lasts only a short fraction of an orbit. Yet the signature survives for 1 billion years as the stream continues to wrap around the galaxy. A brief pull becomes a long-lasting wave in the distribution of stars. Another visual anchor focuses on the directionality of the kink. The stream bends one way, then the other. The S-shape suggests a push that changes sign along the stream. This can happen when the passer crosses the stream at an angle. Stars ahead of the crossing receive one sign of velocity shift. Stars behind receive the opposite sign. The center receives the strongest change. The sides receive weaker changes. The result is a smooth gradient. The small payoff is immediate. The shape of the kink can hint at the passer's trajectory relative to the stream. It can also hint at whether the passer is compact or extended. A compact passer produces a sharper, more localized disturbance. An extended passer produces a broader, softer change. A wandering black hole is compact. Its perturbation is therefore expected to be localized even if it later spreads. The story pauses at a limit of observation that remains specific. Streams are faint. Their member stars can be difficult to separate from the background halo. Distance uncertainties can inflate the apparent width. Proper motion uncertainties can blur the coherence. A feature that looks like a gap may be an artifact of incomplete sampling. A feature that looks like a kink may be projection of a three-dimensional curve. In addition, other perturbers exist. Dark matter substructures can also create gaps and kinks. Giant molecular clouds can do so in inner regions. The galaxy's bar and spiral patterns can also imprint distortions. This is a limit of uniqueness. Morphology alone may not identify the perturber. Models are required. Those models depend on assumptions about the stream's orbit and on the population of perturbers. The calm approach is to seek consistency across multiple streams and multiple features. A black hole perturber should create a characteristic combination of local widening and smooth S-shaped bending. It may also correlate with regions where microlensing events suggest a population of compact lenses. It may align with areas where gas is disturbed into narrow wakes if gas is present. Another small unlock clarifies what can be learned even when the identity is uncertain. Streams can constrain the total rate of strong encounters. They can constrain how many compact masses roam the halo. If streams remain too thin and too pristine, the population of strong perturbers must be small. If streams show many gaps and kinks, the population must be larger. In this sense, streams act as seismographs of the halo's gravitational weather. The weather is not wind. It is the passage of masses through invisible space. The scale shift widens again to the full halo. A single stream traces an orbit. Many streams trace many orbits. Together they form a network that samples the halo. If wandering black holes exist in significant numbers, their passages should be recorded as a pattern of disturbances across this network. The disturbances do not point to a single culprit each time. They point to a statistical presence. The section closes by turning from structure to environment. Streams show how gravity stirs stars. Gas shows how gravity stirs matter that can cool and form new layers. The next step moves into the broader ecological consequences. It follows how repeated stirring can alter the distribution of cold gas and dust in outer regions, and how that slow reshaping changes what future stars and clusters might become. A cold cloud can appear still until a passing gravity field combs it into layers and leaves a faint cavity behind. Wandering black holes reshape the outer environment by stirring cold gas into wakes and gaps that change where future cooling can happen. In that region, a broad sheet of neutral gas drifts through the halo. The sheet is uneven. It contains denser ridges and thinner lanes. Its boundary is sharp on one side and wispy on the other. A visual anchor settles on a ridge where the sheet folds into a shallow arc. The arc is darker along its inner edge. It is brighter along its outer edge. A thin rim outlines the curve like a shoreline. Behind the rim, a hollow appears. The hollow is not empty. It is lower density, a slightly clearer pocket with softer emission. The first small unlock is immediate. A cavity can be carved without a blast. A moving gravitational perturber can create a wake that redistributes gas and leaves a void-like imprint. The core concept is a gravitational wake. It is an over-density trailing a moving mass through a medium. In plain terms, it is a concentration that forms because material is focused behind the parser. The focusing is not symmetric. Gas ahead is pulled toward the track. Gas behind lingers and piles up. The result is a ridge and a hollow that travel with the parser for a time. A short definition keeps it clean. A gravitational wake is a trailing density enhancement caused by a moving mass. The analogy that holds this focusing stays gentle and unique. A slow canoe passing through pond scum leaves a narrow lane and a thin ridge at its sides. The canoe does not explode the scum. It simply displaces and gathers it. The lane remains for a while, the ridge slowly relaxes. In the halo, the canoe is the drifter's gravity. The scum is the cold gas sheet. The lane and ridge are the cavity and wake. This matters because it turns a hidden trajectory into a shape that can persist in gas. Another visual anchor draws closer to the rim. The rim is not a perfect line. It shows small scallops. Each scallop has a sharper head and a softer tail. Along the head, the gas is compressed into a thin layer. Behind it, the layer broadens into a gradient. The gradient fades into the sheet. Fine dust within the layer forms subtle striations parallel to the rim. The physical detail is layering under compression. A small payoff follows at once. Compression can create thin layers that cool more efficiently than surrounding gas, even if the overall environment is hot and sparse. The second concept enters with care and stays narrow. Cooling is the loss of thermal energy through radiation. In plain terms, it is how gas becomes colder and denser when it can shed heat. Cooling depends on density and composition. A wake raises density locally. That can shorten cooling time. A hollow lowers density. That can lengthen cooling time. The drifter therefore creates a patchwork. Some regions become more likely to condense. Others become more likely to remain diffuse. The environment becomes structured by invisible passages. One number anchors the scale of a cavity without leaning on heavy notation. A wake carved in halo gas can extend for about 100 light-years. That span resembles a long chain of star-forming regions laid end-to-end a distance large enough to be mapped as a feature. The scale shift remains calm. The carving occurs through local gradients across a cloud. Yet the resulting lane stretches across 100 light-years and can persist for millions of years before mixing erases it. The near and the far remain linked through slow flow. Another visual anchor shows how the wake evolves. The densest ridge begins to fragment. Small clumps appear along it like beads forming in a cooling thread. Each clump has a brighter center and a softer outer layer. Between clumps the ridge thins. The hollow behind the rim broadens. Its boundary becomes less sharp. The sheet starts to refill. The refill is uneven. It approaches from the sides first. The center remains thinner, longer. The small payoff is immediate. The wake does not simply fade. It concedes substructure by creating zones where cooling and compression are locally favored. These zones can become temporary cold knots that drift and dissolve. Even without forming stars, they change the distribution of cold material. The description stays within the non-human world. There is no observer. There is only a medium responding. A limit of observation arrives and stays specific. Cold halo gas is faint. Some traces depend on absorption against background sources. Without sufficient background density, the sheet can be hard to map. Distance is often uncertain. Projection can make a curved sheet look like a filament. A cavity might be a chance alignment of two thinner regions. In addition, other processes can shape halo gas. Galactic fountains can create shells. Satellite interactions can create streams. Large-scale tides can fold sheets. This is a limit of attribution. The same morphology can have multiple causes. Modelling requires assumptions about the halo's temperature and turbulence. Turbulence can mimic small scallops. It can also erase wakes faster than expected. The calm response is to seek consistent geometry. A gravitational wake tends to align with a plausible track and to show a trailing ridge behind a leading hollow. It tends to have a gradient that points away from the path. It tends to create shear that leaves striations parallel to the ridge. These patterns together can strengthen the case for a moving compact perturber. Another small unlock clarifies the ecological consequence. Cold gas in the halo is a reservoir. It can later drift inward. It can also be stripped away. If wandering black holes repeatedly carve and compress this reservoir, they can bias where condensation happens. They can create cold knots that survive longer than their surroundings. Those knots can later merge with larger flows. They can also be torn apart again by subsequent passages. The reservoir becomes a slowly edited manuscript. Each passage adds a faint line, mixing blurs lines. Yet the overall distribution shifts over time. The scale shift widens to the galaxy's outer life. Over billions of years, many passages can gently stir the halo. They can increase small-scale structure. They can create a more mottled pattern of cold and warm phases. This can influence how gas accretes onto the galaxy. It can influence how stable outer disks are. It can influence how easily thin streams of gas survive. None of this needs bright accretion. It is gravity shaping a medium that is already near a balance. Another visual anchor settles on the boundary between cold and warm phases. A thin interface layer appears. It is smooth on the warm side, it is rippled on the cold side. Ripples propagate along it like slow waves. The wake passes and the ripples linger. The small payoff is immediate. Interfaces remember disturbances longer because they highlight gradients. This is where signatures can be clearest. The section closes by turning from gas structure to the broader question of overall impact. Gas and streams and clusters each provide a partial archive. The next step gathers these archives into a single picture. It follows how populations of wandering black holes change the long-term texture of a halo, and how that texture sets the stage for what a galaxy becomes over deep time. A halo can feel like empty space until many small disturbances accumulate into a subtle texture. A population of wandering black holes can change that texture by scattering stars and stirring gas, leaving statistical fingerprints across vast scales. At this distance, the outer galaxy is a dim volume with faint gradients. The star density is low, the gas is patchy. Streams arc like pencil lines. Clusters sit like soft knots. A visual anchor settles on a wide field where several structures overlap. A thin stream runs diagonally. A diffuse cloud sheet lies behind it. A small cluster glows near one corner. Between them the background is not smooth. It shows gentle mottling. Some patches are slightly brighter, others are slightly dimmer. The first small unlock is immediate. Even when no single drifter is seen, a population can be inferred from how rough or smooth this background becomes over time. The core concept is scattering. It is the deflection of orbits by gravitational encounters. In plain terms, it is how ordered motion becomes more randomized after repeated small pulls. Scattering affects stars and clusters differently. Lightly bound outer stars are easiest to redirect. Dense clusters resist but can still be warmed. Streams are the most sensitive. A small deflection becomes a visible kink. Gas responds by forming wakes and cavities. Each response is local, yet the ensemble response is global. Another visual anchor zooms into the mottling itself. A faint patch of stars shows a slight velocity spread. The spread is not visible as light. It is visible as a broadened distribution of motions. The broadened distribution implies that orbits have been heated. The physical detail that can be imagined is a thickening of a stream. Its edges become less crisp. Its bead spacing becomes irregular. Its center line becomes wavier. The small payoff is immediate. Heating can be detected as loss of sharpness. A pristine stream implies a quiet gravitational environment. A blurred stream implies more encounters. The analogy that holds the idea of statistical roughness stays gentle and unique. A calm beach can look smooth from far away. From closer, it reveals a fine grain pattern created by many tiny waves. No single wave defines the pattern. The pattern comes from the repeated touch. In the halo, the repeated touch is the passing of compact masses. The grain pattern is the distribution of small disturbances in streams, clusters, and gas. This matters because it shifts attention from single events to population-level evidence. The second concept enters with care and remains narrow. Phase space is the combined description of position and motion. In plain terms, it is where an object is and how it moves considered together. Populations leave signatures in phase space because scattering changes both. It widens velocity distributions. It thickens spatial structures. It can create asymmetries where encounters are more frequent. It can also create correlations between location and velocity in debris. A short definition keeps it clean. Phase space is the space of positions and velocities used to track motion. The small payoff follows at once. If phase space is the language of motion, then wandering black holes write in that language without emitting light. Their writing is faint. It appears as broadened lines, softened edges, and slightly warm distributions. One number anchors the idea of rarity that still accumulates. If a single region experiences only a few close encounters over about 1 billion years, the effect can still be visible in the most delicate structures. A few is like a handful of pebbles dropped into still water. Each pebble creates rings. The rings overlap. The surface becomes textured even though drops are rare. The scale shift stays calm. A close encounter is local and brief. The accumulated texture spans tens of thousands of light years. The changes are small per event, yet time is long. The halo is patient. Another visual anchor focuses on a statistical map of stream widths. Across the halo, some streams remain thin, others are thicker. The thick ones tend to pass through regions where gas is more structured and clusters are more disturbed. The physical detail is a gradient in stream width with location. The small payoff is immediate. A correlation between stream thickness and environmental roughness suggests a shared cause. That cause can include a population of compact wanderers moving through the same volume. The story pauses at a limit of observation that remains specific. Measuring population fingerprints requires complete sampling. Streams can be missed if they are too faint. Motions can be uncertain for distant stars. Distance errors can inflate thickness. Selection effect can create artificial gaps and kinks. Gas maps can be incomplete. Different tracers highlight different phases. Models must assume an orbit for each stream. They must assume initial conditions for each cluster. They must assume a background of other perturbers, including diffuse substructure. This is a limit of degeneracy. Different populations can produce similar roughness. A population of dark matter clumps can also disturb streams. Giant gas clouds can do so in inner regions. Tidal effects from satellites can add their own signatures. The calm response is to combine independent lines. Compact wanderers should also produce microlensing events. They should produce a specific distribution of encounter strengths. They should produce localized heating in clusters that matches inferred encounter rates. They should produce wakes and gas where gas is present. No single indicator is decisive. The convergence across indicators is what strengthens inference. Another small unlock clarifies what can be stable even under uncertainty. Even if the exact number of wanderers is unclear, upper and lower bounds can be set from how pristine the most fragile streams remain. A halo with many strong perturbers would erase long, thin streams quickly. The existence of long, thin streams implies limits. Conversely, The existence of multiple kinks and gaps implies some perturbers exist. The population must lie between extremes. The scale shift widens again to cosmic time. Over billions of years, the halo acts as an integrating recorder. It averages over random passes. It smooths the noise of individual events into a persistent texture. This texture can influence future evolution. It can alter how satellite debris mixes. It can alter how cold gas condenses and survives. It can alter how clusters lose stars. The galaxy's outer life becomes slightly more blended. Another visual anchor returns to the wide field. The stream, the cloud, and the cluster remain. Their details have changed. The stream is slightly thicker. The cloud has a faint cavity and a ridge. The cluster has a slightly extended tail. The background mottling remains subtle, yet it is coherent with a story of gentle but persistent stirring. The small payoff is immediate. A hidden population does not need to announce itself with light. It can be read in the softness of edges and the quiet roughness of the halo. The section closes by turning toward resolution. If wanderers can be inferred from textures and rare events, then a final calm synthesis can be made. The next step gathers the arc into a soft landing. It returns to what is known, what remains uncertain, and why the halo's quiet records remain valuable, without needing a dramatic reveal. A galaxy's outskirts can appear quiet while holding a long memory of gentle disturbances. The story of wandering black holes is mostly a story of subtle traces, not of bright events. At this distance, the halo is a low-light landscape. Its structures are faint. They are also persistent. A visual anchor rests on a wide dark field around a galaxy. A thin stellar stream arcs across the frame. Its center line is not perfectly smooth. A small kink bends it by a shallow angle. Nearby, a loose cluster shows a soft extension on one side. Farther out, a cold gas sheet shows a narrow lane and a thin rim. The first small unlock arrives softly. These are not separate curiosities. They are different pages from the same slow record of gravity. The core concept is the wandering black hole itself. It is a black hole no longer bound to a central galactic nucleus. In plain terms, it is a compact mass travelling through the halo on a long orbit. It can be launched by mergers and dynamical interactions. It can also be left behind when the centre changes. It carries no light of its own in most cases. Its influence is gravitational. That influence does not need to be strong to matter. Over time, repeated passes can shape patterns. Another visual anchor draws closer to the stream kink. The kink is sharpest at its centre. The stream's brightness drops slightly at that point. The edges widen downstream. The physical detail is a local widening and a gradient in density along the arc. The small payoff is immediate. A single close passage can leave a kink. The kink then spreads as stars drift along their orbits. This converts a momentary encounter into a long-lived signature. The second concept returns in a calm-bounded form. Scattering is the cumulative deflection of orbits by encounters. In plain terms, it is how a halo becomes a little more mixed and less pristine. Scattering does not erase structure instantly. It softens edges. It thickens streams. It warms clusters. It also stirs gas, creating wakes cavities and thin compressed layers. These effects are small per event. The halo's long timescales make them add up. The analogy that closes the arc stays gentle and unique. A slow breeze across a field of tall grass creates patterns that travel. Individual blades move and return. The field as a whole develops a direction in its texture. The breeze is not seen directly. It is inferred from the way the grass leans and ripples. In the halo, the breeze is the passage of compact masses. The leaning is the collective change in stream sharpness, cluster tails, and gas layering. This matters because it offers a way to learn about dark travellers without expecting a bright flare. One number anchors the calm scale of the record. A single thin stream can remain recognisable for about 1 billion years. That span is like a slow erosion of a shoreline that still keeps its outline across many seasons. The scale shift remains soft. An encounter can last a short time compared with that billion-year persistence. Yet the imprint can remain because orbital motion spreads it rather than erasing it. Time turns local events into extended shapes. Another visual anchor shifts to the cold gas sheet. The narrow lane is bordered by a thin ridge. The ridge shows faint scallops. Behind it, the cavity fades into a smoother gradient. The physical detail is compression into a layer and a trailing wake. The small payoff is immediate. A black hole can alter the probability of cooling and condensation without forming a bright accretion disk. It can make small regions more likely to become cold knots. It can make other regions less likely. This does not guarantee star formation. It changes the reservoir's texture and its future pathways. A limit of observation arrives with clarity and calm. Many signatures are not unique. Streams can be kinked by other perturbers. Gas can be shaped by tides and fountains. Clusters can be heated by many processes. Distances can be uncertain. Faint structures can be incomplete. Models must assume initial conditions that are not fully known. This is a limit of inference. The halo is read indirectly. Yet there are ways to reduce ambiguity. Multiple independent traces can be combined. A population of wandering black holes should create a characteristic distribution of small disturbances across many streams. It should correlate gas wakes with regions where compact perturbers pass. It should produce a pattern of mild heating in clusters consistent with encounter rates. Rare lensing events can add a separate check. The quiet confidence comes from convergence rather than any single dramatic marker. Another small unlock follows. The story does not require certainty about every individual traveller. It requires a recognition that halos preserve statistics. A smooth halo implies few strong perturbers. A textured halo implies more. The presence of very thin streams implies upper limits. The presence of repeated kinks and softened edges implies lower limits. Between these limits, a range of populations can exist. That range itself is information. It informs how galaxies grow, merge, and settle. The scale shift widens to a broader perspective. Over cosmic time, galaxies trade material. They acquire satellites. They reshape their halos. In that long process, compact wanderers act like moving points of stress. Each point is small. The system is vast. Yet repeated motion can influence how debris mixes and how reservoirs of cold gas persist. The halo's gentle roughness becomes part of a galaxy's identity. Another visual anchor returns to the wide field one last time. The stream arc, the cluster tail, and the gas lane remain. The background mottling is subtle. The scene is still. It also feels slightly more legible. The small payoff is immediate. The halo is not empty. It is a medium that holds long echoes of mass in motion. The closing transition stays soft and does not open a new mystery. The arc now rests. The next silence can be filled by the same slow images. A thin stream drifting, a ridge in a gas sheet, a faint tail of stars. Gravity continues and the record continues without needing any bright signal.